Hello, and welcome to my analysis of Lab 1, Motion and Constant Velocity. Now, the purpose of this lab is to study motion under constant velocity, or static equilibrium. This lab is also intended to be an introduction to the tracker software, GlowScript physics computations, and system analysis. And this lab specifically relies on the Newtonian model of physics, which is made up of three underlying laws of motion. The first law states that a body at rest will remain at rest unless acted upon by an external force. The second law states that the force acting on an object is equivalent to its mass times its acceleration. And the third law states that every action has an equal and opposite reaction. Newton's second law will be the most important for understanding this lab. A quick introduction to the results shows that the predicted motion from the computation model and the observed motion measured through tracker are nearly identical. This reveals that computational models can be extremely accurate tools that physicists can use to predict motion in constant velocity. As stated before, force is equal to mass times acceleration. This can be arranged and derived to show the position update formula, where position final equals position initial plus velocity initial plus force divided by mass times a change in time times a change in time. For this specific experiment, the system is an exo marker and everything else is the surroundings. The first half of the experiment has us using Tracker, which is a software that allows physicists to move frame by frame and measure the position of an object. A reference measurement is needed to calibrate the software so the software knows how far an object has moved frame to frame. The time scale must also be calibrated so the software knows how much time has passed between frames. In this video, a marker has been pushed along a table and let go, and the video captures the marker after it has been let go, so there's no further force acting on the marker from a hand. The initial position is 0 meters in all axes. The initial velocity, which was calculated from the slope of the position versus time graph, is 0.4 meters per second in the positive x direction. And the force is 0 newtons in all axes. Now, I chose to center the origin of the axes at the center of the marker. The positive x direction is pointed to the right by standard conventions. However, if this were flipped, a negative sign would be present in the position and velocity vectors, and nothing else would change. Now, the second half of the experiment uses GlowScript computations, where physicists must manually set initial parameters when coding. I set the initial position as 0 meters in all axes, 0.4 meters per second in the x direction for the initial velocity, and 0 newtons in all axes for the force. Now, this code relies on Newton's second law to derive the velocity update formula and the position update formula, as I showed in an earlier slide. And an iterative loop records the final position over a given time interval through small time steps. So a final position is calculated and recorded, then time is advanced, and the next final position is recorded. This happens hundreds of times throughout the code to spit out a final graph which shows the final position over a time interval, predicting the motion of the object through the code. Now, what can we learn? Well, these results indicate that the computational model matches almost identically with the observed results measured in Tracker. And this makes sense because Newtonian physics is an accurate model for describing motion on the scale. So deriving equations from Newton's second law will create an accurate model to describe motion. In this scenario, we are assuming that friction is negligible. This means that we can assume constant velocity when computing a predicted position for the object. Again, since friction is negligible, we know that the gravitational force and the normal force have already canceled out in the y-axis. So the net force acting on the object is 0, which means there's no acceleration acting on the object and the velocity will stay the same. Now, the data from Tracker shows an object that at some point has moved further than expected, as we can see the red line is above the blue line at certain points in the graph. This could be due to a tilt in the table in the direction of motion or user error when tracking the motion in the Tracker software. As stated before, the gravitational force and normal force cancel out in the y-axis. Now, the friction force is technically present and is not being canceled out by any other forces in the x-axis, but it is so small that it is negligible, which means that it does not visibly affect the motion of the marker. So what can we take away? Well, this lab showed that the computational models are extremely accurate when predicting the motion of an object under constant velocity. It is always important, however, to understand the initial conditions and external forces acting on an object. In this scenario, friction was negligible, but that will not always be the case. A strong understanding of basic physics principles is required to analyze the best methods to use when describing the motion of an object. Thank you.